planets in a row, including Pluto. My very excellent mother just sent us 9 pizzas. We're going to focus on these 3, Venus, Earth, and Mars, and the Goldilocks effect, where one of them is too hot, one of them is too cold, and one of them is just right. Hey, which one do you think is too hot? Think about it. Which one's closest to the sun? Venus is closer to the sun, huh? Which one do you think is too cold? Mars. But as we'll see, there's something amazing about Venus. So we're going to highlight. Woohoo! Here we go. You've probably heard about the greenhouse effect and global warming, but did you know that if the Earth had no greenhouse gases, our planet would be colder? In fact, it would be too cold for us to live here. So the greenhouse effect is actually good for us, at least to a certain point. Greenhouse gases act as a blanket that keep us warm because they trap some warm radiation from the sun. Too much of a good thing can be really bad, though. If we had too many greenhouse gases in our atmosphere, we could warm the planet up too much. And as you know, that's what we think we're doing every time we start our cars and turn on our heaters and things, huh? Some nearby planets, Venus and Mars, also have greenhouse gases in their atmospheres. You've heard the story of the 3 bears. This is the story of the 3 planets. Venus is much too hot, Mars is much too cold, and Earth is just right to support life. There is more to the story than you might initially think, though, and your job will be to figure out what other things, what other variables, besides greenhouse gases, affect the temperature of the 3 planets. Engineers built spectrographs for spacecraft that traveled to the planets Venus and Mars. One of the goals was to find out what gases make up their atmospheres. These spacecraft sent data back to Earth. The spectrographs found the spectra of Venus and Mars by looking at light from the 2 atmospheres that originally came from the sun. Hey, look at this graph of Venus while we're talking about this. Would you guess, do you remember we had a couple kinds of spectra? We had an emission and we had an absorption spectrum. Looking at this one, where the light is up here and then it drops down and then goes back up, do you think this would be an emission spectrum or an absorption spectrum? Are we releasing light in a certain wavelength, or are we absorbing, removing light from a certain wavelength? Remember, the emission spectrum was pretty much dark with a few bright stripes on it, huh? And those were the wavelengths of light that were emitted, that were given off. In which case the graph would be low to the bottom and it would have spikes going up. An absorption spectrum, on the other hand, has all the colors except a few that are removed, huh? And so when you make a graph of that, it ends up looking like an icicle hanging down. It's got all these colors of light, but not that color of light. Does that make sense? So this is an absorption spectrum. And what's happening is the atmosphere of this planet, this is Venus, is absorbing that color of light and allowing the other colors to keep going. And so the spectrograph can measure that. It's measuring lots of light in these wavelengths, but not very much in this wavelength. And then lots of light in these wavelengths is coming through. Does that make sense? Emission versus absorption. When you look at a spectrum taken from a spectrometer, you can figure out what is inside of that atmosphere because the dips and peaks in the graph match up to the known dips and peaks of gases that scientists and engineers have measured in laboratories. You will be using actual data from spacecraft and data taken in a laboratory to figure out what is inside the atmospheres of Venus, Mars, and Earth. Is the highlighting going okay? First, let's compare the spectra of Venus and Earth. The spectrum of Venus was taken from the Venera 15 spacecraft with an instrument called the infrared Fourier spectrometer in the 1980s. The spectrum of Earth was taken by the Nimbus 4 spacecraft, which orbited Earth in the 1970s. Hey, this said it was infrared light, huh? Would you be able to see that? No, you can't see infrared. Could you feel it? Yeah, the more infrared you have, the more heat there is. Compare the dips in the planet's spectra with the spectra of known elements on the next page. Be sure to look at the scale very carefully across the bottom. Notice that the x-axis is backwards from what you might expect. Try to find which elements show dips in the same places in the planetary spectrum. So we have these two different spectra, Venus and Earth. Which one looks like an easier spectrum, a simpler spectrum to start with? Which one looks easier to you to read, the Venusian one or the Earth one, the Terran one? Well, I see lots of dips in Earth. I really only see one in Venus. So to me, I think Venus might be easier to start with because there's only one thing to worry about. And about what wavelength is that right there? What number wavelength should that be? Come on, read the numbers. Yeah, it's between 10 and 20, a little closer to 20 than to 10. I think 17 is a good estimate. So let's see if we can look at the next page. Do any of these spectra have a similar dip at about 17 micrometers? What do you think? Which of these has a good match there? Let's see. Carbon dioxide has a dip right about here. Carbon monoxide only has one dip. Methane kind of has a double. I'm going to ignore that one for a minute. And nitric oxide, that's a very complex one with at least 3 major dips. That seems tricky. Water looks a little tricky. Here's ozone. But look at what number is ozone at. Yeah, it's like at 8 or 9, huh? So does that match the number that we saw for Venus? No, it doesn't match. What about carbon monoxide? Does that match? Oh, it looks like it's about 4.5, huh? That doesn't seem like a match. What about carbon dioxide? Is that pretty close? That looks more like 15 than 17, but I think for our purposes, that's a pretty good guess. So would it be fair to say that Venus, the Venusian atmosphere, contains CO2? What do you think? Does that seem to make sense to you that this would be for CO2? Yeah? Okay. Now let's look at Earth. What do we see for Earth? Huh, I see the same kind of a dip right there. But then I see all of this other stuff that we have to explain somehow, huh? All of this also has to be explained for Earth. But it seems to me that this first dip was a pretty good match for that one on Venus, huh? So do you think it's fair to say that this dip is also from CO2, even though it has a little different shape, huh? We could see if there's another overlapping part of the spectrum from another element. And then what do we have? We have another dip at 10. And then we have all kinds of stuff going on around 7 and 8, don't we? So let's look at these other guys. There's our carbon dioxide, a single dip at around 15. Methane. Its biggest dip is just less than 4. Does that match the Earth atmosphere? Not really. It actually is present in Earth's atmosphere, but can we see it on this spectrograph? Can we see that dip at 4? This graph doesn't even go down to 4, does it? So I'm guessing if it did, there would be a dip for methane also, although there's hardly any methane in our atmosphere. So it would be a very small dip. With the data that we have in front of us, can we say that methane is present in Earth's atmosphere? Not with the data that's there. The only thing you could use is the fact that I told you it's present, but I want to stick to the data. Okay? So you should not say that methane is present. What about carbon monoxide? A dip at 4.5. Can we see that on the Earth spectrum? We can't see it, can we? It's off the edge. What about nitric oxide? All this stuff going on, but look at the numbers. 1,500 and 2,000. Does that match what we've seen for the Earth atmosphere? Excuse me, for the Earth's spectrum? Let's see, how high does this go up for Earth? It only goes up to 100, doesn't it? So I don't know how you could tell that nitric oxide was there because Earth only goes to 200, and those dips are all above 1,500, aren't they? So we can skip that one. You see how I'm trying to isolate this down, narrow it down more and more to make decisions about which gases are there and which are not? I want you to make your own decisions about the last two that we have, about whether they're present on Earth or not. Based on all of that, I want you to answer questions 1 through 4 on the next page. Page 14. Does anyone out there have a better plug than this that I can borrow? That'd be great. Oh, darn. This is where you're meeting. So what I like about this is that it's quite a bit like real science, because we can be pretty certain about some things, but then there are other things that maybe yes, maybe no, huh? And the thing with science is that leads us to new questions that lead to new predictions and new experiments to test those predictions and new data, and hopefully we're able to answer with certainty in the future. For example, maybe we could answer this more with more certainty if we had spectrograph that went below 7 or went above 200, right? If we could measure more ranges of wavelengths. So that leads to a new experiment to gather more data to answer those questions. Along the way, there's probably some new questions that result. So it's like a cycle that's always continuing, and different people are contributing different things at different times. How are we doing out there? You got how many questions have you answered? Show me 4 fingers if you've done all 4 of them. Done 4. You've done. Is that a 3? 4. You've done 4. 4. Is that a 3, Laylee? Right? You ready to go? Okay. We're gonna do that together. Do you mind doing that together? Or you want to do it later? I know you're super confident about doing that. How are we doing, Marcus? Are you done with 4 questions? Yeah? Ron? Grace, did you finish?
Yeah, 4 questions.
Hold on. Hurry, because we're going to start in just a minute. Alondra, did you finish 4? Did you finish the first 4? And talk through your mask, okay? You don't have to pull it that down. It just makes it more obvious that you're talking to your neighbor when you shouldn't be anyway. All right. So, I don't know, which is your favorite thing about the science class? The fact that we do highlighting and reading like we're in English class, or the fact that we do calculations as if we're in math class? Because science makes use of all those things, huh? You have to be able to read, you have to be able to write, and you have to be able to do math in order to succeed at science, just like so many other things in life, right? So we're going to try to answer this question. Just how much CO2 do the 2 planets have in comparison to one another? First of all, did we all agree that both planets had CO2 in them? Right? But how much is the question in comparison to one another? And to make a fair comparison, we have to account for some differences between the planets. For instance, have you ever heard something about an ant being 50 times stronger than a human? Yeah, an ant is like 50 times stronger than me. But is that a fair comparison? Can I pick that ant up? Can that ant pick me up? Not with this belly. But for my size, compared to the ant, how much weight can I lift? If I was an ant, I'd be able to lift a car. So we're adjusting for the difference in size, and that's why it's fair to say that an ant is stronger than a person. If an ant was the size of a person, it'd be able to lift a car. Okay? So we have to make some adjustments to make fair comparisons. And that's what we're going to do here when comparing the amount of CO2 on Earth and Venus. Okay? So to start with, part A. Venus has 90 times more atmosphere than the Earth does. The atmosphere is 90 times thicker. Do you remember when you did the auroras assignment? You made a little graph, a diagram with the different layers of Earth, of the atmosphere. And our atmosphere ends about 100 miles up from the planet. Venus, 90 times more than that, like 9,000 miles up from the planet. It has a lot more atmosphere. So automatically it's going to have more CO2, doesn't it? But we want to make a fair comparison here. So what we're going to do is come up with a couple of algebraic expressions to represent the different planets' atmospheres. In algebra, A sub V equals 90 A sub E. What do you think A sub V stands for? What's the A? What are we comparing?
Venus and Earth.
We're comparing Venus and Earth. That's the V and the E. What's the A?
Atmosphere.
The atmosphere. So A sub V is the atmosphere of Venus, which is equal to 90 times, what's A sub E? Atmosphere of Earth. So the first question just asks you what they stand for. And the reason we have to use those subscripts, which I know can be confusing, but we're talking about atmospheres in both cases. So A sub V, atmosphere of Venus, huh? In a minute, we'll get to A sub M, which would be what?
Mars.
Atmosphere of Mars, exactly. Okay, so A sub V, A sub E simply stand for the atmospheres of these two planets. Part B, about 0.04%, very tiny percentage, 0.04% of the total mass of Earth's atmosphere is carbon dioxide. Algebraically, E sub CO2 is equal to 0.0004 A sub E. So the atmosphere of Earth, if we take 0.04% of that, which is this number, that gives us E sub CO2. What do you think that stands for? What's the E?
Earth.
Earth. What's the CO2? Carbon dioxide. So E sub CO2 is the amount of, you should start with that phrase on part B, the amount of what? Yeah, you can just say CO2 if you want. The amount of CO2 where? Yeah, the amount of CO2 on Earth. Part C. Very similar, but different numbers. About 97% of the total mass of Venus's atmosphere is carbon dioxide. So we have the equation V sub CO2 equals 0.97 AV. The atmosphere of Venus was that last part, right? So 0.97 of Venus's atmosphere is the amount of CO2 on Venus. So what does V sub CO2 stand for? The amount of, right. So the first part was just trying to work through the logic of why we use these complicated letters, right? Now we get to do the math itself. Now we can combine these algebraic expressions to find out how much CO2 is in the Venusian atmosphere compared to Earth. Please complete the calculation using this equation. Are you ready? A sub V. What was A sub V? Well, look back at part A. What was A sub V? What number was it? 90. So you're going to put the 90 for this, correct? We don't need to worry about the AE, just use the number. Just use the number. What was the V sub CO2? 0.97. Again, just use the number. Multiply those together on your calculator, please. Doesn't it say to multiply when you have things in parentheses next to each other? Go ahead and multiply 90 times 0.97. Now save that number on your calculator because then you're going to divide by E sub CO2. You have to use this crazy small number. Now, if I've ever taken a point away from you and said show work, it's because I want you to write down on your paper 90 times 0.97 divided by 0.00004 equals. That's how you show your work. You write down what you divided and you write down what you multiplied to get the answer. And you do the math. 90 times 0.97 divided by 0.00004. I think you're going to end up with a big number, aren't you? As I recall, it's over 200,000. Is that right? Now you just repeat that same answer for number 6. It's just using that answer in a sentence to remind us what that number is. In other words, Venus has 200 and something thousand times more CO2 than Earth. Imagine if CO2 was gold. Would we want to go to Venus if it has 200,000 times more gold than we have? Yeah, and then we'd make plenty of our own CO2, wouldn't we? The problem with Venus is the atmosphere is so thick that the pressure is huge. And when we've sent spacecraft to Venus, when they landed on it, they got crushed. Not only that, it's really hot, so they had to withstand the temperature. Not only that, when it rains there, it's sulfuric acid rain. So it's a very extreme environment on Venus. So whatever you got for your answer on part D is also your answer for number 6, correct? Number 7, Venus is also very hot. It can get up to 900 degrees Fahrenheit at the surface, which is hot enough to melt lead. I'm not talking about pencil lead, I'm talking about the metal lead that sometimes we use for plumbing, although hopefully they don't because that has problems too. But it's hot enough to melt lead on the surface of Venus. What reasons can you think of that might explain Venus's hot temperature? I'm actually looking for 2 reasons here. All right, go ahead and write down your answer. Did you have a question or were you offering? Just go ahead and write down your answer. I'm looking for 2 answers here. One of them we talked about at the very beginning. One of them we've been calculating. Check this out. If we look at the order of the planets, what was the closest planet to the sun?
Mercury.
Mercury was closer than Venus, huh? So what do you predict Mercury's temperature is compared to Venus? It's closer to the sun, so we expect it to be hotter, right? But guess what? Mercury is a smaller planet, so it has less gravity. And because of all the energy it gets from the sun, it's actually driven all the gases away from the planet. Mercury has no atmosphere. So can it trap heat? No. Does it get really hot on the daylight side of Mercury? Yeah. But on the nighttime side, it's very cold because there's no atmosphere to trap heat. In fact, Venus is hotter than Mercury. So did you get two reasons that it's so hot? Why is Venus hotter than Mercury? Should be one of those. Yeah, what do you got? Because of the levels of CO2, lots of CO2, and CO2 acts as what kind of gas? It acts as a greenhouse gas, meaning that it traps the heat there, right? Plus, it's pretty close to the sun. Is that what you had too, Jake? Good. All right. Good job, guys. That was part one of Goldilocks and the three planets. Let's do part two, because we've only looked at two of the three planets, haven't we? So we got to go out to Mars now. Now let's look at the spectrum of Mars compared to both Earth and Venus. The spectrum of Mars was taken by the Mariner 9 spacecraft in the 1970s. Once again, compare these spectrographs to the spectra of known elements on page 13. So you're going to have to go back a couple pages. Put an X in the table to show the molecules that are present in the atmospheres of each planet. So in the table, you're either going to leave it blank or you're going to put an X in it, right? With me on that? We're just going to check off the boxes that have that molecule on that planet. We've already done Venus and Earth. What did we find for Venus? Venus had carbon dioxide. I put an X there. Anything else? Or do I just leave the rest of it blank? Leave the rest of it blanks. So see how you're going to do that? Just check off the molecules that are present in each of the planets. Already done with Venus. You can just go to your Earth answers if you don't remember and check off the molecules that are present and then compare Mars to the spectra to take care of it. In fact, when you're done with the chart, there's three questions that should be pretty straightforward for you to answer at the bottom. So go ahead and do that.
I know Mars does have water. Actually. Yeah, it does. They proved it does have water.
In the atmosphere? We're
Oh,
only measuring the atmosphere here, right? So you're right. Mars does have water, but it's all on the ground or underground. And this is only measuring the atmosphere.
no, I don't even know.
Check your questions? Sure.
I'm not too sure. That's all I know.
Oh, I think you've checked too many things. I like the top row. Based on our, remember I told you this is here, but based on our data, we can't see it there. This
Really?
one is all in this zone. Can we see that on Mars? Well, I think you just
Does this look good?
yeah, but again, so I told you guys that methane was present in the Earth's atmosphere, but we did not see it in the data. So you should not check it off. I want you to base this on the spectrograph that we can see. And we didn't see it in the spectrograph. So please don't check off methane just because I said so. Only check it if you see it in the spectrograph. Okay? And then answer the 3 questions at the bottom of the chart. You have to wait for Jake.
Oh, more than Differently, what do we do after answering the three questions?
Then we get to do more math. How are we doing? You got those questions answered? Yeah? Going too fast? All right, so we're going to do that same process of a mathematical comparison, except that we're going to add to that you get to figure out the algebraic expressions that I gave to you before. So let's start by looking back at those earlier expressions. I'm talking about things like AV equals 90 AE. The only thing is, we're not going to look at AV, we're going to look at what? Not the atmosphere of Venus, but we're going to look at the atmosphere of Mars. So we need AM, right? And it will equal the number of times Earth's atmosphere. So we have to find that. Where is that? Oh, here it is. Mars has an atmosphere that is 0.95% the mass of Earth's atmosphere. Write an expression that shows the mass of the Martian atmosphere compared to Earth. Okay, so what was our, what letters are we going to use to represent the atmosphere of Mars? Atmosphere of Mars is going to be AM. Now, I think it'll be easiest for us if we just use a lowercase letter like that instead of doing the whole subscript thing. Is that okay? Does that make sense? Atmosphere of Mars. Then I'm going to hit space. I'm going to hit equals and another space. Only 0.95%. Well, the thing with percents is you have to add 2 more zeros in front of it, huh? So it's not 0.95, it's 0.0095 times Earth's atmosphere. How do we represent that? AE. And I'm just going to use a capital A with a little e. Does that make sense? That's our expression to represent Earth's atmosphere. Next, this is just a repeat of what we did. What part of Earth's atmosphere is CO2? I think we represented that as Earth CO2 equals. With me on that? And it was 0.04%. Now, if it's percent, what do I have to do? I have to move that decimal over 2 places to the left because it's a percentage. So it's 0.0004 times the atmosphere of Earth. Is that okay? Do you see where I'm getting this from? Don't worry, on the test, I would not make you come up with these expressions for yourself. I just want to see, you, I want you to see where they come from, okay? And to think about it for yourself also. What about this next one? I want to know how much of Mars's atmosphere is CO2? Yeah, it's now going to be mCO2 equals what? Be careful. Be careful. What does it say on letter C? 95%. No. Look at the difference to letter B. What did B say? Did it say 4%? No, it said 0.04%, which made it be double zero and a third 04, huh? So for this one, you just move it 2 places to the left and we get 0.95. Are you with me on that? 0.95 times what?
And AN.
Yeah, the atmosphere of Mars. And now we have to combine these together to make that fair comparison. Once again, we're trying to make a fair comparison, just like we did with the strength of the ant versus the strength of a person, right? Got to account for how much atmosphere we both have. Mars has very little atmosphere. So do you guys know, I think I talked a month ago about how they just landed that new probe on Mars, right? Do you guys know it has a drone helicopter on there? Yes, it has a drone helicopter, but the atmosphere of Mars is much thinner than here. So how big do the what do they call them? You know, the parts of the helicopter that spin around, the blades. How big do those have to be if it's a thinner atmosphere? They have to be bigger, don't they? To catch enough air to fly. Not only that, I think it has to have twice as many. So instead of having like 4 blades, it's going to have 8. And they're going to be thick and long so that it catches enough air to fly. I don't think they've tested it yet. They might be doing that just this week. They've never done it before. So it'll be interesting to see if it works, because they had to plan it all out without being there, huh? They had to do math like this to calculate how big those blades were going to be. So what are we going to do? We're going to combine these here to find the amount of CO2 on Earth's atmosphere compared to Earth, right? And it's really the same equation as we used before, except it's Mars instead of Venus. So it's the atmosphere of Mars, how thick that is, much thinner than Earth, whereas Venus was much thicker, times the amount of CO2 on Mars, and then that is all divided by the amount of CO2 on Earth. That's our equation. Now, what are you going to fill in place of A sub M? We have it up here. What is it? What are we filling in place of A sub M? What's it going to be? What number do we use?
95.
Yeah, it's 95, but it's 0095, huh? So it's 0.0095 times what? That was A sub M. Now we need M sub CO2, another 95, huh? But this one is 0.95. 0.95. I'm going to put this in parentheses because we have to do this first. Am I showing my work here? Am I showing you how I'm getting the answer? Instead of just writing the answer down. And then that's going to be divided by the amount of CO2 on Earth, which is what number?
004.
Yeah. 0.0004. Give it an equal sign, and you do the math now. Go ahead, find out that 0.0095 times 0.95 divided by 0.0004, I think. I think you're going to get a very small number this time, huh? That's not that small. But compared to Venus, it's small.
Surely I got this, but I don't know if this is right.
What'd you get?
Oh, it's because I times it, not divided.
Now make sure that when you multiply, you hit the equals button before you start dividing again.
You understood me. I don't know. Wait, I'm slow.
Did you get just a few years older than you are for your answer? From my point of view, it's just a few years between your age and that age. I guess that, from your point of view, that's half of your age, isn't it?
I got this.
Yeah. Oh, I didn't get that. I got those numbers, but I didn't get that decimal point. I got 20 in some.
I don't know why I keep doing wrong then.
Okay, well, let's check check these. Did you go 0.0095 times 0.95, then hit the equal sign, divided by 0.0004, 1, 2, 3 zeros, and then the 4, then the equal sign, and you should get something in the 20s.
Oh, it's because I put only 1 0.
Yeah?
I put double zeros, not triple zeros.
Yep, I had a feeling that was the case. Okay, answer questions 5, 6, 7, and 8.
Walkers.
So this is your homework, questions 5 through 8. You've got not quite 10 minutes to get as much done as you can to reduce the amount of homework you have to do. And that will be the end of Goldilocks and the Three Planets.